And welcome back to Unit 11. In this part of Unit 11, we're going to learn about angular variables. We're going to start with angular position. Angular position is a measure of the angle through which something has rotated. Okay, so if I have something moving in a circle, your angular position would be the angle which something has rotated through. You can relate angular position to quantities you're more familiar with, the radius of the motion and the distance traveled along the arc, that is usually given the letter S. Angular position is related to the distance traveled along the arc S through S equals R theta. Okay. The next question we might ask is, well, how quickly did it go through this angle? That's a measure of angular velocity. Just as we had for linear velocity, angular velocity has two forms. It has the average angular velocity, which is found by taking the change in angle over the change in time. Or we can ask about the instantaneous angular velocity, which is found with a derivative of the angular position with respect to time. And lastly, we can ask, is the angular velocity constant? And if it is not, then we have an angular acceleration. Angular acceleration also has two forms, an average angular acceleration, which is a change in angular velocity over a change in time, or we can look at the instantaneous, which is the derivative of the angular velocity with respect to time. Hopefully you're seeing here that the relationship between the angular variables is very similar to the relationships with the linear variables. So, for example, angular acceleration is derivative of angular velocity with respect to time. Linear or tangential acceleration is the derivative of the velocity with respect to time. And this is what we learned in the second unit, I believe. Now, just as the linear variables are vectors, so are the angular variables, but the angles are the directions are not going to be what you would think. So what are the directions of the angular variables? Let's draw another picture, putting the x-axis coming out of the page, the y-axis, let me draw that better, more typical at least. The y-axis points, positive y points to the right, and the z-axis points upward towards the top of the page. If I have an object rotating in the xy plane, let's say it's here, coming around, here's my angle theta, I can define two vectors in the plane of the page. One is the radial vector, which points outward. The other is the vector for the arc length. Vector for the arc length points perpendicular to the radial vector, which means it's tangential to the circular path. It has to hold true that the direction of that arc length vector is going to be the direction of the angular variable, angular position, crossed with the direction of the radial vector. So what vector can I cross with this r hat to give me s pointing as shown? And the answer there is going to be that this has to be in the positive z direction. So remember from the previous video, to take and find a direction for a cross product. I point my fingers in the direction of the first vector, in this case theta. I'm arguing that it has to point upward. The r vector is pointing kind of out, kind of to the right. So I'm going to point my palm in that direction, allow me to flip my fingers down and point in that direction. And that gives me S pointing a little bit to the right and a little bit inward. Okay. So I can use the right-hand rule and the cross product to determine the direction of these vectors. Now I'm going to make a little change here because this isn't just based on the unit vectors, it is actually true for vectors in general. I can write a similar expression for the angular velocity and the angular acceleration. So all of them, all of the angular variables are going to be directed perpendicular to the plane of rotation. In this case, the picture I've drawn, the plane of rotation is the xy plane, and omega, alpha, and theta will point perpendicular to that, which is meaning they're going to be either in positive z or negative z. Okay. Just as we had before, if omega and alpha are in the same direction, then omega will increase. And if omega and alpha are opposite each other, then omega will decrease. This is how I speed up and slow down my angular velocities. We can relate the linear variables to the angular variables. We've already written down how to get from angular position to arc length, S equals r theta. And we know that if I take the derivative of arc length, that's going to give me velocity. But that's equivalent to d by dt of r theta because S equals r theta. If we assume that the radius is constant, it pulls through the derivative, and I have d by dt of theta, but that is simply r omega. So now if you look, I have the tangential velocity is going to be r omega. And I can do a similar piece by taking the derivative of that velocity. That will give me my tangential acceleration. So that'll be d by dt of r omega, or r d by dt of omega, which is r alpha. So the tangential acceleration is the radius times the angular acceleration. Next, I would like to look at these accelerations because we have 3 accelerations we've dealt with this semester or this class. One just the tangential acceleration. So a tangential is the derivative of the velocity. Okay. This is what we dealt with when we were looking at the centripetal motion and the fact that we can be moving at a circle and speeding up. That gave us a piece of the acceleration that was in the direction of the velocity and a piece of the acceleration that was perpendicular to it, one causing the velocity to increase, the other one causing it to change direction. Okay. We also have the centripetal acceleration. That one we found was v squared over r. And I can take and plug in that v equals r omega and get an alternate form for this. That's r squared omega squared over r, or r omega squared. So I can write the centripetal acceleration in terms of either the velocity, the regular velocity we've dealt with all semester, or the angular velocity at any given instant. And lastly, I have the angular acceleration. That's going to be the derivative of the angular velocity And as we saw on the last slide, also can be written in terms of the tangential acceleration by taking the radius and multiplying by the angular acceleration. Lastly, I would like to do an example applying all of this, thinking about the Earth. Okay. What is the angular speed of a point on the Earth's surface at a latitude of 69 degrees? What is the linear speed at the same latitude? And what latitude would you have to be at to have a linear speed of 92 meters per second? Okay, so first off, let's draw a pretty picture. Here is the Earth and the equator. We have a latitude of 69 degrees. That is telling me this angle is 69 degrees. There's the axis of rotation. Okay. This side of the angle, or triangle, is the radius of the Earth. Okay. I will need this to do part B and a similar one to do part C. Let's start with part A. The angular speed of the Earth, well, that is the change in position over time. In 1 day, the Earth rotates through 2 pi radians, and you must work in radians when working with angular position. And that's in 1 day, 2 pi radians in 1 day, taking and converting days to seconds. Oops, that's a 24-hour times 1 hour is 3,600 seconds. This gives me an angular velocity of 7.27 times 10 to the minus 5 radians per second. Now notice in this calculation, I didn't have to use the fact that we were at a latitude of 69 degrees. And that's because the Earth is a solid object and all of it rotates together. It all rotates together. Therefore, every point on the Earth's surface has an angular velocity of 7.27 times 10 to the minus 5 radians per second. Not only that, but every point within the Earth, the sphere, the globe that forms the Earth, has to have that angular velocity because it all rotates together. Okay. For the linear speed, I can get it by taking V equals R omega. Now, the R in this case is not the radius of the Earth, but the distance from the axis of rotation, which is this dotted line I drew up above. Okay. Well, how far is that side from the axis of rotation? We have a triangle. This is RE. Here is the R I want. If this is 69 degrees, then this is also 69 degrees. And we can see that R will equal the radius of the Earth times the cosine of whatever angle that is. For part B, that angle is 69 degrees. So I'm going to write R as RE cosine of 69 degrees times omega. But we're told the radius of the Earth is 6,378 kilometers, doing a unit conversion to meters there, times the cosine of 69 degrees, times 7.27 times 10 to the minus 5 radians per second. That gives that the velocity, how fast a point on the surface at this position is moving, to equal 166.2 meters per second. Part C is very similar, but we want to find the latitude. We want to find the angle. In this case, we know that V is 92 meters per second. R is going to be, again, RE times the cosine of an unknown angle, and then times omega, which is still 7.27 times 10 to the minus 5 radians per second. If I take and solve this for the cosine of the angle, that gives me that cosine of theta equals I didn't write down that number. I'm sorry. It gives me cosine of angle equals a number. And I can find that theta, once I put it all into my calculator, equals 78.5 degrees. To find this number, which I don't have written down, I need to take the radius of the Earth, multiply by the angular acceleration, angular velocity, and divide it by, or divide v by it. So it would look like this, v divided by RE omega.